Hey, this is Horner, and we are looking at gravity and Coulombs law. Free response question number 4. You have two spheres, 1 and 2, and they carry amounts of charge and have masses that are not necessarily equal. And we can see they're not equal because they have a separation distance. They're connected to the same point in the ceiling by strings of different length and remain at rest in equilibrium as shown in case A. Later, sphere 2 is removed. We take this out. We put sphere 3 in. And when we do that, we notice that the system changes. So now our number 1 is further from the vertical line and 3 is closer. So it's kind of the opposite of what you see in case A. Both diagrams are to scale and have a grid, so that will help you see the relative angles and the lengths of the string. So the 4 circles below represent case 1 and 2 in case A, and then 1 and 3 in case B. They want us to draw and label the weight force, or the force due to gravity, tension force T, and electrostatic force E on the sphere. Use the grid to draw the forces with correct angles and relative components. Don't draw any components on the force vector. So here what we're going to do is take a look, and we see that in this first case the force of electricity is going left and going right, and it should be equal and opposite. The tension, though, in this one is going to be greater because it's closer to the center. Okay, the tension force here is not as big. The tension force here is not as big, and that's because there is more force due to gravity pointing down, and so it should be looking like this. So this right here, this distance, which is 1, 2, 3, 4 blocks, is the same as the 1, 2, 3, 4 blocks pointing F down for FG. Notice in this one, FT is smaller. It's only 2 blocks up, and it's because we only have 2 blocks down for FG. In case B, everything switches. Now I have more tension in this one, and I have less tension in this one. So you'll see the tension here and the tension here. And it's because this one's got to be more massive. If it's more massive than this is, you'll see kind of how that works out. And because it's more massive, it's got that bigger FG, so it's got the bigger FT. So it's a little bit counterintuitive because usually the same mass, as you pull it out, will create more tension. Okay, but in this case, we're not thinking about the same mass. We're thinking about the relative masses between the two. In the spaces below, they want us to rank the spheres in terms of their mass. So 3 has got to be the biggest. Notice that it has the biggest force of tension, followed by number 1, which is here. Okay, so it's got the next biggest force of tension. And then finally, number 2. Is it possible to rank the spheres in terms of their charges? No, you can't do that. And here's why. The force of electricity is the same in size and in correct direction. Sorry, that's for this up here. For this down here, the force of electricity is applied to both, regardless of the bigger charge. So it doesn't matter what the charges are, the force of electricity is the same. But because one of them can have a bigger gravity, the sphere with the more vertical tension has more mass. So there's more vertical tension, you'll notice, in this one and in this one. So those have to have more mass. Okay, and that's kind of what's going on in this problem. In a well-organized paragraph, we have to justify that. We said that the force of electricity is applied to both regardless, and then we said that the sphere has more vertical tension, has more mass, and then you have to just say as shown in that free body diagram. That's why it is the way that it is. And that is the end of this problem.